We're going to be using our knowledge of all of the trig identities that we've learned, and also we're going to be working with our background in algebra with some factoring to solve trigonometric equations. So to get started, let's go ahead and look at some trigonometric equations, and we'll look at some strategies for working with trigonometric equations and solving as well. First thing I'd like to do is to kind of do a quick review of some algebra. If we had an equation like x squared plus 2x plus 1 equals 0, I could factor this into x plus 1 times x plus 1. There's many different ways that you can factor. This is kind of the reverse FOIL or a trial and error message. But if you were to FOIL this out, you'd get back to x squared plus 2x plus 1. And then what we use is called the zero factor property. And the zero factor property basically lets us look at taking each of the factors and setting it equal to 0 to solve. So this is called the zero factor property. In order for the zero factor property to work, there has to be a 0 on the right hand side. And then what I can do is I can take each of these factors, and these duplicate, and set them equal to 0. There's no way that I can have two numbers multiplied together and get 0 unless one or both of those numbers are 0. And then if we solve from here, I'd subtract 1 from both sides and I'd get x equal -1, and of course the same here. So our solution to this equation would be x equal -1. So that's the zero factor property. Now, not everything will factor nicely with the reverse FOIL method. Sometimes you're going to have to use something called the quadratic formula. And the quadratic formula will actually work on the problem that we just did as well. The quadratic formula works on anything that's to the second power. But what we want to focus in on is trying to factor first if we can. If that doesn't work, then we'll go to the quadratic formula. So the quadratic formula looks like x equal -b plus or minus the square root of b squared minus 4ac all over 2a. So you definitely want to memorize this one. This is going to come in handy. So if we can't get it to factor using the reverse FOIL method, then we might go to the quadratic formula. And I'm sure you've all worked with the quadratic formula before, and we'll be seeing it here momentarily as well when we're working with a problem. So what I would like to do is to just jump right in and look at some problems, the same type of problems that you'll see in your My Math Lab homework and also in your handwritten homework and exams. Something to keep in mind, you still need to know your unit circle, so if you don't have that memorized yet, make sure you have that written out somewhere or drawn out somewhere so you can refer to it. Let's go ahead and look at our first problem, 3 cotangent of x plus 1 equal 4. Now, quick note, if I don't put parentheses around the argument of my trig function, it becomes a little bit confusing about, is this just x or is it x plus 1? So when you're working, please always put parentheses around the argument of your trig function to make it clear. Now in My Math Lab they don't do this, and so it gets a little bit confusing, but when you're working, please always do that. Now here, what we're asked to do is solve the equation. And there's an infinite number of solutions here, so we have to be given some sort of a interval. So over the interval. And this interval will go from 0 to 2 pi. Now because we're going from 0 to 2 pi, I can assume that I'm working in radians. If this had said 0 to 360 degrees, then I would assume I'm working in degrees. So this one I'll assume I'm working in radians. So the first step I'll take is I'll isolate the variables in the trig function. So isolate the trig function. So I'll subtract 1 from both sides to get started. And again, this is a review of algebra. 4 minus 1 is 3. Divide both sides through by 3, and I get cotangent of x equals 1. Now if I wanted to, I could take the inverse cotangent of both sides, or you can think about what your unit circle looks like. Now cotangent equal to 1, I know this is going to be a pi over 4 multiple. It's going to be 45-degree multiple if you'd rather think in degrees. But cotangent is positive here, and if cotangent is positive, that must mean I'm in the first or the third quadrant. So these are the two quadrants where cotangent is greater than 0. So I'm looking at two solutions. One in quadrant 1 and one in quadrant 2. So my Q1 solution would be pi over 4, and my Q3 solution would be 1 pi, 2 pi, 3 pi, 4 pi, 5 pi over 4. So my solutions here, I always list my solutions from smallest to largest. pi over 4 and 5 pi over 4. Now this is in terms of radians because I was asked to find solutions over the interval with the radians. So when I'm working with these, the first thing I always try and do is isolate the trigonometric function. If I can't do that, I try and factor. If I can't do that, I use the quadratic formula. And I guess another method would be finding the greatest common factor as well, and we'll run into a problem that's similar to that. In fact, I think it's the next one that we have up, so let's go ahead and have a look at it. Let's look at 9 sine squared theta times the tangent of theta plus 9 sine squared theta equals 0. And I want to find solutions over the interval from 0 degrees to 360 degrees. So here I'm definitely working in degrees and not radians. So before we isolated our variable, but you can see on this problem I don't have just a single variable to isolate. So what I'm going to look for here is the greatest common factor. So the greatest common factor can be abbreviated GCF, greatest common factor. And if you look to see what's common between both of these, it looks like they both have a sine squared theta. And oh, there's a 9 as well. So let's go ahead and pull out the 9 sine squared theta. If I factor out the 9 sine squared theta, I'm left with tangent of theta plus 1 equals 0. And I always like that 0 on the right when I can get it when I'm factoring, because then I can use the zero factor property. So now what I have here is I have two numbers or two expressions multiplied together that give me 0. So what I can do is take each of these and set them equal to 0. So I have 9 sine squared theta equals 0 and tangent of theta plus 1 equals 0. Divide both sides through by 9, I get sine squared equals 0. Take the square root of both sides and the sine of theta is 0. Now over here I'll subtract 1 from both sides and I get tangent theta equals negative 1. So basically I need to solve each of these now. This says between 0 and 360. So let's talk about sine. Sine is positive in the first quadrant and the second quadrant. So let's make note of that. So I should have an angle in the first and the second quadrant for the sine equation. And then tangent theta is negative 1 in the second quadrant and in the fourth quadrant. So tangent's negative in second and fourth, sine is positive in first and second. So if we talk about where the sine is equal to 0, that's actually going to be a quadrantial angle. So sine theta equals 0. Sine is equal to 0 at 0 degrees. So theta equals 0 degrees and at pi. And then again at 360, but this is not a bracket, so I can't include 360. My other option is tangent theta equals negative 1. That's going to be a multiple of pi over 4. So in the second quadrant, that would be 3 pi over 4. And then in the fourth quadrant, that would be 7 pi over 4. And then when I finish up my problem, I always write all my answers. Whoops, I'm combining radians and degrees here. I need to be careful. So let's pop back over here. 0 degrees and 180 degrees. And then 3 pi over 4 would be 135 degrees in quadrant 2. And then quadrant 4, that would be 315 degrees. Now when I write my answer, at the end I list these in order from smallest to largest. So that would be 0 degrees, 135 degrees, 180 degrees, 315 degrees. So those are my answers. And again, we list these in order from smallest to largest. So there's an example where we looked at the greatest common factor before we got started with the problem. Let's go ahead and look at our next problem. And again, the more of these that we work, the easier these will be because we'll start seeing some patterns. So I want to make sure we can work through a lot of these. Let's look at negative 2 sine squared x equals sine of x minus 1. Now this is how you'll see it in my math lab. It's a little bit confusing. Is that minus 1 part of the argument? Is it transformation or not? It is not part of the argument, so we'll put parentheses here. But again, when you're working, please always put parentheses around the arguments of your trig function. Well, right away I see we can't isolate a variable. We can't get sine by itself. We can't solve for sine then. I can't factor out a greatest common factor. So it looks like to me I'm going to get everything and set it equal to 0. So I'm going to move everything to the right, and the reason I'm doing that is I want this leading coefficient to be positive. So when I do that, I'd have 2 sine squared of x plus the sine of x minus 1 equals 0. So again, what I did is I moved this across. Now my hope is that this will factor. 2 sine of x times the sine of x, and then 1 and 1, and I want my plus sign to be positive, so this would be positive and negative. So let's double check it. Yep, it works. So you're going to have to practice your factoring if you haven't factored in a while. Now that I have this set equal to 0, and again 0 is the important part here, I can take each of the factors individually and set them equal to 0. And again, it's very important that you check your factorization to make sure that's correct. Here I'd add 1 to both sides and then divide by 2. Here I'd subtract 1 from both sides, so I'd get sine of x equal negative 1. Now on this one I forgot to write out all the instructions, but for this one let's go over the interval of 0 to 2 pi. So we are working in radians. Okay, so for here, sine of x, that's a 30 degree, but since we're working in radians, we'll call that pi over 6. So this would be pi over 6 and 5 pi over 6 in the second quadrant. And then the sine is negative, equal to negative 1 at, sine is equal to, that's 3 pi over 2. There's only one angle that we have that. So I have 3 solutions here. They're already in order, but I'll rewrite them. X equal pi over 6, 5 pi over 6, and 3 pi over 2. Those are my solutions. Now if you're curious if you're right about these, you could take pi over 6 and plug it into the original on the left, get a decimal approximation, plug it into the original on the right, and get a decimal approximation to check that as well. And again, if you're doing these on your calculator, you need to make sure you're showing all your work and all your steps, because that's really what you'll be given credit for. Let's go ahead and look at another one. Let's look at tangent squared of x plus 9 equals 0. Now remember, we do have some restrictions about what sine, cosine, tangent, etc. can be equal to. Well, if we isolate the variable in this case, I would subtract 9 from both sides. And right away I can look at this and I can think there's no solution. And the reason there's no solution is, what number can you square and get a negative 9? You might think, well, what about 3? Well, 3 squared is equal to a positive 9, and you might say, well, what about a negative 3? Well, that's negative 3 times negative 3, which is another positive 9. So these don't, I can't get the negative 9 that I need out of this, so it's no solution. If you tried to take the square root of both sides, you get tangent of x equals the square root of a negative 9, and you might say, well, that's okay. Tangent x would equal plus or minus 3i then, but we are not working in the complex number system. We would be solving this over the interval of, let's say, 0 to 2 pi, which are not complex numbers, these are real numbers. So no solution, because I'm trying to take the square root of a negative number. I'm trying to take the value, I can't find an angle whose tangent after being squared added to 9 is 0. So be careful, not all of these are solvable. Okay, let's look at another example. Sometimes they give you these in factored form already, and that's very nice of them. Sometimes they look a little bit different, and they don't have the same variable for both of the factors. So let's look at one where we have cotangent squared theta plus 4 cosecant squared, or sorry, let's just do 4 cosecant theta equals negative 5. Now there's a couple things going on here with this. First of all, we have cotangents and cosecants. So we don't have a common factor here, and on the right hand side we don't have a 0. We don't have this equal to 0, we have it equal to negative 5. So I need to do some work on this. So the first thing I think it would be a good idea is to rewrite this. Excuse me, I'm not sure what that was. It was your old video. Let's look at cosine squared of theta over sine squared of theta plus 4, and then cosecant is 1 over sine of theta, and this equals negative 5. So I think what I would like to do here is to find a common denominator. So the common denominator would be this sine squared. So here I'd multiply top and bottom by sine. And here I'd have to multiply top and bottom by sine squared. Now once I have that common denominator, I can essentially drop it. It would be the same thing as multiplying through everything by sine squared. So this would look like cosine squared of theta plus 4 sine of theta equals negative 5 sine squared of theta. Okay, so now what I want to do is I want to try and get everything on one side, but I also need to think about, this is really kind of confusing because I have sines and cosines. Wouldn't it be nice if this was all sines or all cosines, one of the two? Well, I think it'd be easiest to turn everything into sines because of this cosine squared. Remember, sine squared plus cosine squared is equal to 1, one of our nice Pythagorean identities. And if I solve this for cosine squared of theta, I get 1 minus sine squared of theta. So I'm going to take this and I'm going to rewrite it as 1 minus sine squared of theta. Then I'm going to get everything on one side of the equation and get it set equal to 0. Now I like my leading coefficient, my highest power, to have a positive coefficient if I can. So I'm going to move this 5 sine squared theta, and I'll line that up because they're like terms. And I'm going to end up with 1 plus negative sine squared plus 5 sine squared is 4 sine squared theta plus 4 sine theta equals 0. Now this is looking good because I have 0 on the right hand side now, and on the left hand side I have everything that I can in terms of sine. So let's go ahead and rewrite 4 sine squared theta plus 4 sine of theta, and I'm going to put this plus 1 equals 0. Now the reason I rewrote that with the plus 1 at the end is because then it looks like a nice little trinomial that I should be able to factor. So this looks like to me it will factor into 2 sine of theta plus 1, 2 sine of theta plus 1. And again, if you're not strong with your factoring, take a second and make sure that you can factor that, because it's going to be really important that you be able to factor these quickly and kind of focus on the trig and not so much the factoring. Next step is I could take these factors and apply the zero factor property and set them equal to 0. Now if you notice, these are the same factor. So if I solve for sine theta here, I'd subtract 1 and divide by 2. I'll get the same thing here. So it's a repeat of the same factor. It's a repeated root. So I don't necessarily have to go through the process of solving for that. Once I have one set of solutions, I should be good to go. So this is saying sine of theta is negative 1/2. Okay, well, where is sine negative? Sine is negative in quadrant 3 and in quadrant 4. So this is where sine is less than 0. And I don't remember in our original instructions, no, I don't have anything about the interval. So let's, on this one, do 0 degrees to 360 degrees. So let's work in degrees instead of radians. Well, this has to be a multiple of pi over 6 because the sine of pi over 6, or the sine of 30 degrees, is 1/2. So it has to be some sort of multiple like that. So in this case, theta would equal, it'd be 210 degrees. That's the angle that has a reference angle of 30 degrees. That's in the third quadrant. And in the fourth quadrant, that would be 330 degrees, or 11 pi, sorry, yeah, we're in degrees. So 210 degrees and 330 degrees. And these are already in the correct order from smallest to largest, so you're good to go. So sometimes you might have to rewrite these, and you might have to apply an identity, in this case the Pythagorean identity, in order to simplify this to the point where you can actually solve. Okay, let's go ahead and look at another problem, and in this one, hopefully it'll factor. I don't know. We've had everything would factor very nicely so far. Let's look at 12 sine squared of theta minus 6 sine of theta equals 5. And we want to solve this over the interval of 0 to 360 degrees. So right away I know I'm working in degrees and not radians. Okay, so you could start setting these up if you wanted to and start thinking, well, it could be 12 sine theta, sine theta. Actually, this won't even work yet because I have to get 5 over on the left-hand side. So let's go ahead and subtract the 5 across. So once I start setting these up and keep trying all the different combinations, and again, it is trial and error. You might try a 5 and a 1. You might try a 4 and a 3 and a 5 and a 1. This does not factor. So you can try all the different combinations for 12 and then all the different combinations for 5 for each of those combinations of 12, but basically this doesn't factor. So because this doesn't factor nicely, we get to use the quadratic formula. So when you use the quadratic formula, it's always a good idea just to write it down in its generic form before we start to populate the equation. Now, something I'd like you to do is I'd like you to think about substitution. So let's go ahead and let x equal sine of theta. So what ends up happening then, this nicely rewrites to 12x squared minus 6x minus 5 equals 0. Now this is a lot easier to work with when it's in this form than dragging along the sine theta. And then what I can do is at the very end of the problem, go back in and resubstitute back. So far, A is 12 here, B is negative 6, and C is negative 5, because this is the standard form ax squared plus bx plus c equals 0. Okay, we'll leave a little bit more room. So x is equal to negative b. So I need the opposite of b, so I need the negative and the negative 6. The negative 6 has to be in parentheses here when I square it. If I did negative 6 squared, that would be a negative 36, but what I really need is a negative 6 quantity squared, which is a positive 36. So those matter, it makes a difference. Minus 4 times a times c all over 2a, 2 times 12. So let's go ahead and simplify. So negative 6 times negative 6 is a positive 36. Negative times a negative is a positive. 60 times 4 is 240. All over 24. So this is going to be x equals 6 plus or minus the square root of 276 all over 24. Now 276 is not a perfect square. There's probably some factors I could pull out to try and simplify this, but I really don't think that that's what our focus needs to be here, because we're trying to solve the trig part of this, but we can simplify it a little bit. So x would equal to 6 plus or minus. Now when we look at the factors of 276, we can see that it's even for sure. And maybe that there's some other factors as well, but I think maybe a 4 might pull out. So let's call this root 4 root 69 all over 24. X equals 6 plus or minus the square root of 4 is 2. Square root is 69 over 24. Then what I can do from here is factor out a 2. And then the cool part about this is the 2 cancels into the 24 12 times. And so this is a little simpler, but I still have a fraction, so I don't know what we gain by simplifying. But this is a little simpler to look at. So this is what the expression is that I have. Now we have to remember what was x? X was sine of theta from up here. So x was sine of theta. So I'm going to say, okay, sine of theta equals 3 minus the square root of 69 over 12, and sine of theta equals 3 plus the square root of 69 over 12. Now this is not real easy to solve because I don't have a nice number that's a nice standard angle. So what I can do here then is I can come up with a decimal approximation for the right hand side, and then I'll have to take the inverse sine of that. So to get started, I'll have theta equals, or what I could show is the inverse sine or the arc sine of both sides. Okay, and then over here on the left hand side then I get theta equals, and let's pull our calculator in. So I'm looking at the arc sine or the inverse sine, and am I supposed to be in degrees or radians? Okay, so up here I'm in degree mode, and my calculator I'm in degree mode, so I'm okay there. And I'm going to use my alpha y equal key, and I'm going to go 3 minus the square root of 69 all over 12. So this is, remember, this is saying what angle has a sine of 3 minus root 69 all over 12. And this is telling me it is negative 26.2455, etc. Now this is in degree mode, which is what we want to be in, so let's copy this down. Theta is equal to negative, whoops, that kind of popped away. Theta is equal to a negative 26.2455 2597. Now this isn't my final answer. I'll show you what we need to do with this. Remember, this is an inverse trig function, so this is the angle that's between negative and positive pi over 2. So what I need to do is to figure out what are the angles that match with this that are between 0 and 360 from up here. So this is a reference angle. Now if my sine is negative, because 3 minus the square root of 69 over 12 is negative, what I need to do is to figure out which quadrants that's in and then use that as my reference angle. Now this gets a little bit complicated, but it is kind of interesting and fun as well. So let's look at what we have here. So sine is negative because this value right here is less than 0. It's negative. So where is sine negative? It's negative in quadrant 3 and in quadrant 4. Now I need to find the angle that's the reference angle. So I need this reference angle to be the 26.24552597, etc. So that's going to be 180 degrees plus 26.24552597. And then there's going to be another one over here that has that same reference angle. And that's going to be that 26.2455, etc. 2597. So that's going to be, there's a couple different ways we could think about it, but I think the easiest way would be 360 degrees minus 26.24552597. So again, we need to know where we're at in terms of the unit circle. So if I calculate both of these, and let's say our answers need to be rounded, if we read the directions, they might say something like round to the nearest tenth, so we'll round to the nearest tenth. So let's take 180 plus, and I don't need to carry it out all the way. I'm just going to take it out 3 places since we're rounding back to 1 decimal place. I'll take it out 4 places. So that would be 206.2 degrees. So theta equals 206.2 degrees. That would be the one that's in Q3, the third quadrant. And then my other one would be 360 degrees minus that. So let's do 360 minus the 26.2455. So that would be 333.7545, which is 333.8. Now that's just from one of these. Now we need to work on the other one. So on our other one, I think I'll change the color of just this so we don't get them confused. So on our other one, I could take the inverse sine of both sides. And this is going to be a positive value. So I'm going to be looking for where the sine is positive. So this would be theta equals, so let's go ahead and take the inverse sine of 3 plus root 69 over 12. So if I wanted to, maybe I could go up here and just copy this and then change that to a plus. So here I get 70.42755 degrees. 70.42755 degrees. Now remember, this is our reference angle. So what I'm going to do is I'm going to see where is the cosine, or sorry, where is the sine positive, and that's in quadrant 1 and quadrant 2. So this is where the sine is greater than 0, sine is greater than 0, and the neat thing about this is its own reference angle will be here at that 70.4 degrees. And then the other one will be over here, clear over here, and this reference angle right here is 70.42755 degrees. So to figure out my other one, I'd take 180 minus 70.42775. So let's do that. So 180 minus 70 point, there it is right above, 42755. So that's 109.57, which would round to 109.6. So those are my answers. Now there's a lot of work involved in this. I'm not kidding you at all, especially with that quadratic formula. If you have a mistake in the quadratic formula, it throws everything off. So I'm going to show you how to check these answers as well. But before I do that, let's go ahead and write these in order from smallest to largest. So that'll be 70.4 degrees, 109.6 degrees, 206.2 degrees, 333.8 degrees. So I think these are my answers. Is there any way to know if that's true? Well, one thing that you could do is that you could plug everything back into the original equation and check. Now it looks like we need to go back here to the beginning in order to check our answer here. 12 sine squared theta minus 6 sine theta minus 5 equals 0. So this is what I want to check right here. Now I have to check this when it's set equal to 0, because that's the way our calculators work. It has to be set equal to 0 to solve, or that's one of the ways that we can do this. I think it's probably the easiest way. So that's the equation we're trying to look at. Now when I graph this, what I want to look for is where it crosses the x-axis. So this is to check. So I'm going to graph and see where it crosses the x-axis. Those are my solutions. Now a couple other things. When you put this into your calculator, and I'll show you how to do this in a second, the way the calculator uses this, I can't put the sine squared right here. The way it enters it is sine, theta, and then on the outside of the parentheses is squared. And it's really confusing because do you mean you're squaring the theta or do you mean you're squaring the sine? So the way I prefer to enter this, just to make sure that I am doing it correctly, I don't like to write sine theta and then put the squared on the outside. I like to just write the definition of sine squared, which is sine theta times sine theta. So this is what I'm going to graph. So let's go ahead and pull that graph in. So I'm going to clear everything out. I graph by going to y equal. I'm in degree mode up here, which is where I want to be because that's my problem was solving between 0 and 360 degrees. So I want to graph 12 sine theta sine theta. I'll just use x as my variable. I can use that shortcut key here. Minus 6 sine x minus 5. And again, in order to use this, in order to graph, in order to find where it crosses on the x-axis, you really need to make sure this is set equal to 0. So this is important. And then we want to go to our window, and remember I'm going 0 to 360 degrees here. So let's start at -5, let's say. And again, I'm in degree mode up here. And let's go to 375 because I want to be able to see a little bit on each side. And the x scale here that's shown, okay, I wanted to go by units of 1, let's say, and then the max and the min I'm not so interested in. So let's go ahead and hit graph. So this is what the graph looks like. It's crossing once, twice, 3 times, 4 times. So it says it has 4 solutions. Now how do we find those solutions? Well, let's go ahead and take a screenshot of this first. blow it up quite a bit. And I also want to go back in and I want to get a screenshot of the equation that we graphed. I guess it kind of cut it off, so that won't help. So what I want to do is to find out what these points are. And the way our calculator does this, the trace function doesn't work. The trace gets really close, but it doesn't tell us exactly. We want the exact value, so what we do is we go to second calc, which is above the trace function, and we go to 0, because we want to figure out where it's crossing, where y is equal to 0. So it says right bound, and so see where I'm to the right? I'm going to clear that out. I don't like how I started that. So I'm going to go to second calc, 0, and down in the left hand corner here, see where it says left bound? I want to go clear over to here to the left to see what's going on. And do you see that star moving? So there's to the left of that point. Let's move to the right of that point and hit enter. And there's our first guess. It's given right here. It's 70 point something there. And if you notice that 70 point something, if we round that to the nearest tenth, it matches with up here. So that's that 70 point something. Let's go back and let's find this one right here. So we go second calc, 0 again. Now where it says left bound, we want to be to the left of that second point. And then it says right bound, and we want to be to the right of that. Hit enter one more time, and it says 109.577. Now you're probably thinking, man, this is going to be fabulous. I don't even need to solve any of these. But you have to. You have to show your work because that's where you're being given credit. So showing your work is really important because, again, that's where your points come from. The answers are pretty easy to come by if you're using your calculator. So, again, it's really important that you show your work because that's where your points will come from. Now let's find this third point where it crosses, second calc, 0. I'm looking for left bound of that. And it can be any point that's to the left. Right bound. It's requesting right bound. And it says 206.24553. Okay, and then let's find this final point over here. So again, second calc, 0, and these are great ways to check your answers but not to do your work. Okay, it should be popping out of the sky here in a second. Okay, so left bound and then right bound, 333.75. And there's our last answer. So let's see how these compare with what we did for our handwork. Okay, so for our handwork, we had 70.4, which matches right here. So this is that 70.4. We also had 109.6, and that matches here. Then this crossing point was here at the 206.2, it looks like. And then this last point was 333.8 degrees. So these perfectly match our hand solutions. I would always recommend checking these whenever you can, but you can't just use these as your answers because you won't have any credit. You have to do the handwork and then use your calculators to check. A couple quick things I want you to be noting is here, do you see I have the 1.3 times e? It's actually times 10 to the negative 12, whereas these have zeros. So this means essentially 0. Your calculator is trying to approximate this, so that's why it's called the 0 function that we're looking at. Those are as close to 0 as your calculator could get with estimation. So some of these problems you can see, if you're going to use a quadratic formula, are very, very long, but very, very doable at the same time. So one of your questions in this will be asking you particularly to make sure to use your calculator And when you're using your calculator, make sure you're in the correct mode. If it's asking for your answer to be in degrees, make sure you're in the degrees. If it's asking for your answer to be in radians, 0 to 2 pi, make sure you're in radian mode. So these are very doable. Make sure you sharpen up those algebra skills with factoring, and you shouldn't have much trouble. But if you do, as usual, please feel free to send me a text. You're welcome to send me the problem from my math lab in your work, and I'm happy to help you out. And you're also welcome to use the Pearson Connect to a tutor as well if you feel like you might get better help from there. So good luck on this assignment, and we'll also be working on part 2 to this on our next assignment.